All right, everyone, let's take a quick look at chapter 3.2, the so-called logistic regression. I hope that some or many of you will already have heard of this in a stats class or somewhere else. We will take a very brief look at the theory behind it, but we are, of course, in this class more interested in the statistical software in R, so we'll spend more time on logistic regressions in R, and in this video I will just give a very brief introduction. So again, this is just a remark of caution. Shortened theory, please take a statistics class if you haven't done it already, or read a book or a paragraph online about it. In general, what's maybe most important for you to understand, the application of a logistic regression model is a classification problem with a binary outcome variable, so a variable that can only take two values, yes or no, or 0, 1. And we need a logistic regression model here because the linear model just fails to do this. If we look at this example on the left for the linear regression, we have our data points here, and some of them have a y value of 0 and some of them have a value of 1, and we want our regression line to understand this pattern, to get the perfect fit. But what we see, first and foremost, what's very important, our linear line will just exceed the boundaries of 0 and 1, which is really problematic. I just said we have a binary outcome variable, so our outcome variable can only take the values 1 and 0. So this linear regression model, it does really not fit a binary outcome classification problem. Much better, we take a function of a logistic form, this kind of S-shaped curve. Doesn't need to have this shape, but this is the basic example, and we can also see that this pattern is picked up much better. And of course, if you tweak the parameters, the exact shape of this regression function can be moved or can be altered. In general, similar to linear regression, we get this general formula or standardized function of our regression model. It's not as important that you know this or perfectly understand everything. Basically, you just wanted to show you that we have beta 0 and beta 1 again here. So we have regression coefficients and we have our intercept again. They are just not as they are in the power of the e function down here. So they are definitely not as straightforward to interpret and understand as in linear regression, where they are just multiplied with the value of their x variable, but they are in some kind of a weird position, which also means that the interpretation of a logistic regression model is not as straightforward as a linear regression. So we'll take a more thorough look into possibilities for interpretation in the video that covers logistic regression in R, but just to help you to understand why it's maybe not that easy to interpret. If we have the relationship between a set of variables x, or let's say one variable x and a variable y, here in a linear regression model, so this is our linear regression line, then we have this slope, and it can be interpreted if we go one step to the right. On the x-axis, we have this slope of 2, so it on average increases our y variable for 2 points. If we take another step here from 3 to 4, it will be the same because this is linear. It's already hidden in the name. This slope will always be the same. But for our logistic regression, the regression function could look like this. And the slope is definitely not the same at every point on this function as it is for the linear regression. For example, here we have a slope of 5. Here we have a slope of 2. Slope of -3, even a negative slope is of course imaginable. So as it's not a linear model, we can't just estimate a regression coefficient and then interpret if we increase x by 1, then y will be increased by 1. Because if we, for example, are here at x equals 0 and move one step to the right, so we increase x by 1, then okay, we have this slope of 5, but if we do this over here, move another step to the right, we decrease y. So the interpretation is definitely difficult, but of course we always have some opportunities to do that. First of all, a short theory on how to run this thing in R. Again, we assign our model to an object. It's always like this in R. And the function is GLM. It stands for Generalized Linear Model. And again, we specify our dependent variable. Our outcome variable needs to be a binary outcome variable, else it doesn't make sense to run the linear regression, the logistic regression, sorry. And then you separate it by the tilde. We then just list our independent variables separated by pluses. And to have this logistic regression model for binary outcomes, we just specify that family equals binomial, so binomial outcome variable. In this example, we have an interesting outcome variable. It's called biopsy, and it is data for on biopsies conducted with women that had a tumor, cervical tumor, and the doctors or the data classifies this tumor whether it's malignant or benign. Maybe if you don't know the terms, malignant, it basically means a bad tumor, and the benign means a maybe not so bad tumor, not as deadly. So this is this classification variables that can take the values 1 and 0. And if we run this regression model, we can again print ourselves our coefficient table with the summary function. We just apply the summary function on our model. We just specify it here. And if we use the $ coefficients option and specify estimate and standard error, we get our coefficient table with just the estimate of the coefficient and the standard error of the coefficient. And here we had these independent variables. So for example, whether the woman took hormonal contraceptives, whether the woman was smoking, the number of previous pregnancies, the number of diagnoses on STDs, and so on. So with respect to interpretation, I can just give you two good tips how you can interpret what can be interpreted in a table like this. First of all, the sign, so whether the coefficient is negative or positive. We can in general say if a coefficient is negative, it has a negative effect on the outcome variable, on the dependent variable. If it's positive, it has a positive effect on the dependent variable. And using the standard error, but it's not straightforward written in here, we can also interpret the significance, of course. So we looked at this in the previous video. It's of course always important for us to understand whether a regression coefficient is significant at all or not. And with respect to visualization, of course, this is also not as easy. One thing we can do is we can use a scatter plot and just plot our data and plot the regression model that we fitted. And then another thing that we can visualize is the so-called ROC curve. ROC, it stands for Receiver Operating Characteristic. And this is a curve that where each point on each of these continuous lines is for one logistic regression function or logistic function that could have modeled our data. And of course, each function, if you look at this on the left here, we have a correct and incorrect classification of our model. So we can have a continuous, like a countless different logistic models, and each of them would classify our tumor biopsies, and each of them would of course do correct predictions, so which contributes to the true positive rate. So a bad tumor that has been classified as bad by the model, and the false positive rate. So a not bad, so a benign tumor that has been classified falsely as malignant. So of course we want to maximize our true positive rate and minimize our false positive rate. This is depicted in this dot here, so this would be the perfect classifier model. But in reality we have a continuum of models we can choose from, and we would like to optimize we would like to strive for the highest true positive rate and the lowest false positive rate. So we can, depending on our wishes, if we prefer a high true positive rate or maybe very low false positive rate, we can understand which model on the spectrum of models serves us best. So this was it, as just a very brief and very short introduction to logistic regression models. We will look at them and how to run them in R in more detail in one of the next videos on R.